structure of a K vector space. Okay. So what is K field? So R at a ring. Let's take commutative ring with identity. Okay. And in another set. So what is a module? Okay. V space R module. So the module structure consists of these two maps, R times M product, the scalar product and the addition. So you can observe these two are very much same. The only difference is that you are replacing K by R. Okay. So in particular, if K is a field, K module over K is basically a vector space over K. Okay. Okay. So let's write down the proper definition of an R module. So this is sort of a warm-up class. Okay. R is a commutative ring with unity. Let M be an abelian group. Let M be an abelian group such that multiplication, addition and multiplication defined as above satisfies the following. So we have gone through, we have studied vector space over field. Just a vector space like structure over a ring is an R module. Okay, satisfies the following. So first is that 1 times M is M. R1 plus R2 dot M is basically R1M plus R2M. R plus M1 plus M2 is RM1 plus RM2. Ritik, have I missed something? Have I missed some missed some property?
I'm checking the
No, I think
R1 R2M equals to R1 into R2M.
right. Who is it?
Ovik.
Good. Okay. So it's like this is the vector space structure. So for a few examples, one, any abelian group G is a Z module. Okay. Because you see, they will satisfy each and every one of them. Okay, right? Any abelian group G is a Z module. So by definition, any R module M is basically a Z module because M is by definition taken to be an abelian group, right? So you can, check this thing. Like take R1 and R2, G1, G2, this from Z, this from G, and you can check the rest. R1 R2 are integers, right? So R1 plus R2G, it is of course like R1G plus R2G. No? Sorry. It is of course R1G plus R2G. No? Vibhushan, are you getting it?
हाँ दादा
See, in an abelian group, suppose you do 2G plus 3G, what do you get? You get 5G, na? That's it. The structure is very obvious. Now you do 2 into 3 into G, that is 6 into G. Okay. These are pretty obvious. You are quite late actually. So we are discussing modules like R modules, okay? We are discussing R modules. Ankit, do you know what an R module is? Hello?
Sir, your audible is not
Hello?
clear.
Is that so?
Yes, sir.
Wait a minute. Is it clear to everyone
Yes.
else?
Yes, sir.
क्लियर तो क्लियर আছে তো দাদা
Clear.
Okay, so now is it clear?
Yes, sir.
Yeah, so basically we are discussing what an R module is. R is a commutative ring with unity. So you know the definition of an R module? Hello?
No.
Then don't be 15 minutes late in the class, na? See, you know what a vector space is like, okay? What a vector space over a field K is like. So replace V by M, M is an abelian group, and replace K by R, where R is a ring, and do the same structure, okay? So above you see a K vector space structure. Now here we replace K by R and V by M, and we get this structure. So this is the definition of an R module. Just look at it. I give you 2 minutes, okay? I'm giving you 2 minutes to look at this. Look at it. we have gone through it? So any abelian group G is a Z module. Okay. To any Z to the power n is a Z module. So, but getting back to vector spaces, so we all know the definition of a vector space, right? Let's see. So basis So what about basis of a vector space? What about this? So the question is, does any vector space have a basis? So what is the question? What is the answer? Every vector space has a basis,
Yes.
right? So answer is
Yes.
Why? How to prove it? So how to prove it? So let V be any vector space over K.
Dada,
Go ahead.
actually, in this proof, actually, in this proof, whether we use John's lemma,
Yes, correct. So first define a basis, okay. So basis. Beta is a basis of V if any vector small v in capital V can be written as a spanning set. So beta is a spanning set of V if any vector in V, any vector V in capital V can be written as a finite linear combination of elements in beta, that is V is summation Ci alpha I, where is a finite sum, okay. Ci belongs to K and alpha I belongs to beta, okay. And what is independence? So beta, or maybe a subset beta of V, beta is a subset of V, huh? A subset beta of V is said to be a finite is, I mean a finite subset. Just a minute. So a finite is of V, I mean a finite subset of V is linearly independent if say S is this alpha 1 to alpha n, okay. If summation lambda I alpha I equals to 0 implies lambda I equals to 0 for all I. So any linear combination of these vectors is 0 will imply that the coefficients are individually 0. Okay. Clear? For an infinite, but this definition is for a finite set, right? So for an infinite set beta, we say beta is linearly independent if every finite subset of beta is linearly independent. Okay. Clear? Beta is a basis of V if beta is a linearly independent spanning set of V. Okay. So that's the definition of a basis. So we will first prove the existence of a basis in any vector space, and then we will see why. Then we will see a few things. I mean, why the dependence, linear dependence, independence is defined this particular way. So existence of a basis. Okay. So take alpha belongs to V, non-zero. Okay. So alpha is linearly independent, right? Singleton alpha is linearly independent, no? Right?
Yes.
B option clear?
Yes, sir.
So by L alpha you denote the set lambda alpha where lambda belongs to K. That is basically if alpha is here, you just taking the straight line passing through alpha. Okay. The vector, the one-dimensional subspace spanned by alpha. That's it. Okay. So define sigma to be all subspaces. Vibhushan, you know the definition of a subspace, right?
Yes, sir.
Which has a basis. Yes sir, yes sir করে যাচ্ছিস কেন তুই?
ইংলিশে বলছো তো ইংলিশেই বলবে।
Okay, so sigma is non-empty, right? Sigma is non-empty, right? As L alpha belongs to sigma for any alpha not equal to 0, right? So sigma is non-empty. Okay. Let's check a chain here. So suppose W1, W2 is a chain in sigma. Okay. Define W. What is W? That is union Wi, right? Is a subspace of V, but we further claim that W has a basis. Can you claim what the basis is? So if beta I is a basis of Wi, beta equals to union beta I is a basis of W as for any V belongs to W, V belongs to Wj for some j, implies V is in the span of beta j, right? Which is a subset of beta. Clear? Again, let S is subset of beta I. Okay? Sorry, S is a subset of beta. We will show that S is linearly independent. Okay? I mean, S is a finite subset of beta. So see, we will see that beta spans W and beta is linearly independent. Okay? Yes. 37 মিনিট পরে ক্লাসে কেন বাবা?
দাদা খেতে গিয়েছিলাম, লেট করে দিল।
ওই করো, খাও, ঘুমাও, নেশা করো, ক্লাস করে লাভ নেই। পরের বার যে লেটে আসবে তাতে আমি ডাবল ফিস চার্জ করবো, কারণ দ্বিগুণ সময় তোমার এমনিতেও লাগবে নেট পেতে। এবার কি করা যায়? আমি এতক্ষণ ধরে যে আলোচনা হয়েছে, মানে কি বলবো এবার বোঝা? You know the definition of a module, right? Nikhil, you know the definition of a module, right?
না দাদা, মডিউল ঠিক জানি না।
ডেফিনিশন জানলেই হবে, আর কিছু না।
হ্যাঁ, ওইটুকু।
ডেফিনিশনটা দেখে নে তাহলে। Have a look at this definition. Look at this definition and the example below. That's it. You have 2 minutes. Tadari kor.
ঠিক আছে। দেখে নিয়েছি দাদা।
Okay, so Nikhil, now we are about to prove the existence of a basis of a vector space. Okay, so please look through this quickly. See, this is not a problem solving class, right? Like you can go through and see the previous problems before. Since I am going with the flow, if you are joining the class in the middle, you will struggle to understand a single thing. So please go through this. Done?
হ্যাঁ দাদা।
Good. এটা ইয়ে তো নিখিল তো?
হ্যাঁ।
So we are about to prove that ছাতার মাথা। মানে আমি বুঝি না এটা কেন ঠিকঠাক জায়গায় আসে না কার্সারটা। Again, suppose A is a finite subset of beta. Now you see, so what is beta? That is union beta I, right? Now remember, I mean, what should I say? I mean, how should I put it? Since this is a finite subset of beta I, okay, so what about this? Subset of beta I, yeah. So consider span S. Okay? Span S is basically I mean, so if S is alpha 1 to alpha n, span S is basically the set summation lambda I alpha I, okay, where lambda I belongs to k. That is, you are taking the plane spanned by the vectors of alpha I, okay. So span S is contained in span beta, I mean span S is contained in W, right? Right? See, S is a subset of beta. Maybe I should write like this. So span S is a subset of span union beta I, right? Which you can take to be like span beta I union. Okay. So span S is containing some Wj, okay, which means okay, but there is a small problem. Like yes, span S is containing. This means S is subset of beta J. This is clear because S is contained in this union. Okay, clear. Span S is contained in Wj, which is span beta J, and S is also contained in this. So by that we prove any finite subset of beta is linearly independent. So S is lin int as beta J is linearly independent. Okay. So beta is a basis of W. Okay. So W belongs to sigma. So every chain in sigma has an upper bound. This implies sigma has a maximal element by Zonslim. Okay. See, so our claim is that V is a maximal element, or maybe I should write V is the maximal element. Okay. If not, then there exists some proper subspace. What should I write? Subspace নাম কি দেওয়া যায়? V naught of V, which is maximal in sigma. Okay. Right? So take V naught or maybe alpha from V minus V naught. Okay. Since V naught has a basis, say beta naught, see that beta naught union alpha is a basis of V naught plus, you know plus, right? These operations you are aware of, right? Okay. I am boxing this line. Okay. There is a reason. We will see. Tell me why it is true. Why it is true?
বলবো কারণ V0 বেসিসটা হচ্ছে আমরা বিটা জিরো ধরেছি, আর এল আলফা যেটা হচ্ছে ওটা আলফা থেকে স্ট্যাক করা যে সাবস্পেসটা পাচ্ছি সেটা। তো V0 প্লাস এল আলফা যে কোনো এলিমেন্ট আমরা নেবো সেটা বিটা ইউনিয়ন আলফা থেকে স্প্যান করে আমরা পেতে পারি। আর বিটা ইউনিয়ন আলফা ওটা মানে যে সেটটা ওটা লিনিয়ারলি ইন্ডিপেন্ডেন্ট হয়ে যাবে।
হয়ে যাবে, এটা বিগ ট্রিকি। I mean,
মানে যদি আমরা কোনো ওর লিনিয়ার স্প্যান নেই বা লিনিয়ার কম্বিনেশন নেই ইকুয়াল টু জিরো, তো যদি ইকুয়াল টু জিরো ধরে নিই আর
so
পুরো
basically
একটা
he is using a few facts. Okay, he is using a few facts like A is a subset of B. Alpha is not in span S. Okay. Then no. First of all, we have to see this fact one. Why the name independence? I mean, why these vectors are called independent? So S is linearly in depth if and only if no element in S can be written as a finite linear combination of the others, right? But see, this is not obvious. Okay, this is not obvious because we have defined it in a different way. So basically you see, so if suppose f is linearly independent, okay, so for this part in proof, for this part it is obvious, like suppose you take what, suppose you take so suppose like you take alpha belongs to S, and suppose alpha can be written this way. Okay, I learn it from what way? Okay, where alpha is in S. Okay, suppose alpha can be written in this way, then the problem you get is that summation lambda I alpha I learn from 1 to n minus alpha is 0, right? Right? Since S is linearly independent, you get lambda I equals to 0 for all I, and you get minus 1 equals to 0, right? Because this is a linear combination, na? Finite linear combination, which is a contradiction. And for this part, so you take, so for this part, if alpha, again, if alpha is summation lambda I alpha I, that is if alpha is being written as a linear combination of these, then you get summation lambda I alpha I minus alpha to be 0. Okay? So, but not all coefficients are 0, right? Are 0, which implies S is not linearly independent, right? So this is an if and only if condition. We will need it. And the next fact he uses is that, so if alpha is not in span, we are using alpha a lot, right? Gamma. If gamma is not in span S, S is linearly independent. S is lin ind. Then S union gamma is lin ind. Okay? He is using this very neatly. Why? Because again you see gamma, if gamma is this linear combination, alpha I belongs to S, then if gamma is, if S union gamma maybe I should write like this. So
S union gamma যদি linearly dependent হয়।
If V belongs to S union gamma and V belongs to S, we have nothing to show. If V equals to gamma, if V equals to gamma, then gamma cannot be written as a linear combination of elements in S as gamma is not in span S, right? Thus S union gamma is linear. From the fact 1, right? Now these two he is using to claim that this is linearly independent, okay? And you can see any element, okay? So first of all, this is linearly independent, okay? And any element V belongs to V naught plus L alpha is of the form V equals to V plus lambda into alpha, right? Where summation Ci alpha I plus lambda alpha, where alpha is in beta naught. Thus this thing is in span beta naught unit alpha, okay? So what do we get? We get V naught plus L alpha is in sigma, right? Which is a contradiction, because V naught was the maximal element, right? So alpha was chosen from V minus V naught, right? So that's incorrect. So V is V naught. Clear? Okay. Now here is my question. You think about it for 2 minutes. Question. Replace K module, replace K vector space by R module. No, question is if R module M, if S is a subset of M, it is linearly independent, okay? We are taking that definition, the first definition. For linearly independent, we are taking this definition, okay? For linearly independent, we are taking this definition, okay? And fact 1 was clear about fact 1, like S is linearly independent if and only if elements in S cannot be written in terms of the others, right? Is fact 1 true? This is question number 1. Question number 2 is alpha is not in span S. Oh, that was fact 2, right? Fact 2, no? Yeah, fact 2. Question number 2 is fact 2 true? I am giving you 3 to 4 minutes, okay? Think about it.
দাদা
Okay, so what do you think? No. Okay. So take R equals to Z, M equals to Z. Okay. And take alpha equals to 2. Now you take, take S equals to singleton 2. Okay. Okay. So what is span is? That is 2Z, right? And you can see 2 is linearly independent, right? I mean 2 into A is 0 implies A is 0. Okay. So this is linearly independent. But if you take three, this is outside 2Z, right? Right? But this is not linearly independent. I mean 2 union 3, I mean 2 comma 3 is not linearly independent. Why? Because 2 times 3 minus 3 times 2 is 0. So linear combination is 0 even though the coefficients are not. So this is about fact true, right? So for fact 2 this is.
দাদা বলছি তুমি যেখানে আগে যে প্রুফটা করেছিলে একবার একটু উপরে স্লাইডটা যাবে ওই যে ফ্যাক্ট ওয়ানটা যেখানে প্রুফ করেছিল এই যে হ্যাঁ -1 = 0 তুমি এখানে বলছো কন্ট্রাডিকশন হচ্ছে তো এখানে আমি এমন একটা ফিল্ড যদি নিই সেখানে ধরো -1টা 0 সাথে সমান তাহলে তখন তো কন্ট্রাডিকশনটা আসবে না।
Okay. So homework, in no field -1 is equal to 0. Okay, এটা homework. ঠিক আছে ঋত্বিক, দেখে রাখবে।
ঠিক আছে।
Okay, so his question was -1 equals to 0 is a contradiction only if -1 and 0 are not same. Like he is asking like 1 and -1 is same in Z2, right? So 2 and -1 is same in Z3. So does there exist a field where -1 and 0 are equal? So my questions show that in no field -1 is equal to 0. So linearly independent. Okay. And what about fact 2? Just because two things are linearly independent, I mean, so what was the thing? Like, if two things are linearly independent, you cannot write one thing by the other, right? So for fact 1, so again, for fact 1, so 2 and 3 are linearly dependent, right? Dependent, right? But these are not scalar multiples of one another. Like 2 is 2 by 3 times 3, and 3 is 3 by 2 times 2. But this 2 by 3 is not in Z, and this 3 by 2 is also not in Z. Okay. So even though linearly independent doesn't mean one is the scalar multiple of the other. Clear? Now you understand why there may not exist a basis of a module.
Yes.
So that's the power of field. You see, in a module, in a ring, this 1/3 doesn't exist. This half doesn't exist. The fact that you can't divide in a ring makes a whole lot of different complications. Okay? Remark. And module M may not have a basis. Okay, so this was our warm-up class today. I will probably spend another class with this things, but I am gonna give you some homework. See, this class, since this is a net batch, you will have to go through a few things on your own. This is our textbook of M.Math. This is our textbook of M.Math. And I know that all of you have done these things already, vector space. So I request you guys to go through vector space, dimension, tuple. These are very basic facts, and there are a ton of examples. So I request you guys to go through this chapter. There are some theorems and all that. What was the theorem? So these things I request you to go through. We mainly will see. I can't go by the theory line by line. That's not possible. Okay. Like how to extend a basis, why every basis is those are like conditions, like maximal linearly independent set, basis, these are all same. Okay. So I request you guys to go through this. This can be challenging for devotion only. For the rest of you, this is supposed to be pretty easy, because this is VSC level stuff, and you have, I'm sure you have gone through this sometime in your life. Because from the next to next class, we will start linear transformation. So I request you guys to go through this, please. Okay? Don't disappoint me. Yeah, go ahead.
Can you kindly explain me that why an R module M may not have a basis? The reason?
You can't divide in R. I just showed you. I mean, okay, your question is that Z has a basis, right? By 1. So Z has a basis. Z has a basis, but they are okay. So you want an example of an R module where it doesn't have a basis, right?
Yeah, exactly.
Okay, so that is tricky. Okay, that's quite tricky, and we will do things in the module theory class in Ph.D. Okay, but that's not something you need in the net course. So remember this problem and ask in the module theory class. That's a good question.
Okay.
And even like this, I think of you know, like f to the power n is isomorphic to f to the power m, where f is a field, it implies n implied by m equals to n, right? But is it true for R?
Yes.
Like if R to the power m is R to the power n, does it imply m equals to n? One part is obvious. I mean, if n equal to n, this is obvious. But if R to the power n is equal to R to the power n, does it imply m equals to n? So there are things. I mean, we will go through this in the module theory class. Don't worry. Okay. So that's it for today. But I request you guys to go through the chapter 2. Okay. And we will spend only one more class on that chapter 2. And in the next one, I mean in the third class, we will move on to, what should I say? What was that? Linear transformations. Okay. Okay, that's it. Tata.